Tonight, we're going to try to answer what sounds like the simplest question in all of physics. How big is a photon? A single particle of light. You'd think this would be straightforward. After all, photons are the most abundant particles in the universe. They're everywhere. Every time you open your eyes, trillions of them flood into your retinas. Every star you've ever seen sent them hurtling across space to reach you. We've measured them, counted them, and built entire technologies around them. But here's the problem nobody tells you. When you actually try to pin down the size of a photon, when you ask how much space one of these things actually occupies, the answer doesn't just get complicated. It breaks everything you thought you understood about what it means for something to have a size. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something everyone does without thinking about it. You picture light as a thing, a small thing. You imagine photons as tiny little specks, almost like microscopic bullets fired from a flashlight or a star or a candle flame. They fly through space in straight lines. They bounce off mirrors. They hit your eye. They're little particles of light, and particles have sizes. That's how we've always thought about things. You pick up a marble, you can feel its edges. You look at a grain of sand, you can see its boundaries. You examine a speck of dust under a microscope, you can measure its diameter. Everything in your daily experience has a size. It has a beginning and an end. It takes up a specific amount of space. And so, naturally, when someone tells you that light is made of particles called photons, your brain does what it's always done. It assigns a shape to them. It gives them edges. It imagines a tiny, round, glowing ball, something like a miniature marble made of light, zipping through space at an incredible speed. Maybe you picture it as yellow or white. Maybe you think of it as impossibly small. Smaller than an atom, but still a thing with a surface, a boundary, a definite physical extent. This image is so natural, so intuitive, that most people never question it. And why would they? It seems to work. Light travels from one place to another. It hits surfaces, it reflects, it refracts, it can be blocked by solid objects. All of this seems consistent with the idea that light is made of tiny projectiles. In fact, this is almost exactly what Isaac Newton proposed more than 300 years ago. Newton believed that light consisted of what he called corpuscles, tiny particles that were emitted by luminous objects and traveled in straight lines through space. His corpuscular theory could explain reflection quite nicely. When light hits a mirror, the particles bounce off, just like a ball bouncing off a wall. It could explain shadows too. Light particles travel in straight lines, and when an opaque object gets in the way, it blocks them, creating a shadow behind it. Newton's authority was so great, and his theory worked well enough for so many everyday observations, that the corpuscular model dominated physics for over a century. But there were problems, and they started showing up as soon as people began looking more carefully at how light actually behaves. In the early 1800s, a British physician and polymath named Thomas Young performed one of the most important experiments in the history of science. He took a beam of light and passed it through two narrow slits in a barrier. If light were truly made of tiny particles, you'd expect to see two bright lines on a screen behind the barrier, one for each slit. But that's not what Young saw. Instead, the screen displayed an interference pattern, alternating bands of bright and dark. bright where light from the two slits arrived in sync, reinforcing each other. Dark where the light arrived out of sync, cancelling each other out. This is something only waves do. If you've ever watched two sets of ripples on a pond meet each other, you've seen interference. Where the peaks coincide, they combine to make a bigger wave. Where a peak meets a trough, they cancel out. Young's experiment showed that light does this too. Light interferes with itself, which means it behaves like a wave. This was a direct challenge to Newton's particle theory. Young's experiment, along with subsequent work by Augustin Jean Fresnel and others, convinced most physicists by the mid-1800s that light was a wave, not a particle. James Clerk Maxwell delivered the theoretical framework in the 1860s when he showed that light is an electromagnetic wave, a self-sustaining oscillation of electric and magnetic fields that propagates through space at about 300,000 kilometers per second. Maxwell's equations united electricity, magnetism, and light into a single elegant theory. Light was a wave, case closed, except it wasn't. In 1900, a German physicist named Max Planck was trying to solve a problem about the radiation emitted by hot objects. Classical wave theory predicted that a perfectly absorbing object, what physicists call a black body, should emit infinite energy at short wavelengths. This clearly doesn't happen. Planck found that he could fix the mathematics only by assuming that energy isn't emitted continuously, like a smooth wave. Instead, it comes in discrete chunks, tiny packets he called quanta. Each quantum of energy is related to the frequency of the radiation by a simple formula. Energy equals Planck's constant times frequency. But 5 years later, Albert Einstein took Planck's idea and ran with it. Einstein was trying to explain the photoelectric effect, the observation that when light shines on certain metals, it knocks electrons loose. The puzzling part was that the energy of the ejected electrons didn't depend on how bright the light was. Making the light brighter knocked out more electrons, but each individual electron had the same energy. What mattered was the color of the light, its frequency. Below a certain frequency threshold, no electrons were ejected at all, no matter how bright the light was. Classical wave theory couldn't explain this. Einstein proposed that light isn't just emitted in quanta, it exists as quanta. Light is made of individual packets of energy, particles of light, which we now call photons. Each photon carries a specific amount of energy determined by its frequency. When a photon hits an electron in the metal, it transfers its energy to that electron in one lump. If the photon's energy is high enough, the electron gets kick free. If not, nothing happens, regardless of how many low energy photons you throw at the surface. Einstein's explanation worked perfectly. It earned him the Nobel Prize in Physics in 1921, and it brought particles back into the picture. So now we have a strange situation. Thomas Young showed that light is a wave. Einstein showed that light is a particle. Both experiments are correct. Both results have been confirmed countless times. Light is somehow both a wave and a particle at the same time. This is what physicists call wave-particle duality, and it's one of the most fundamental features of quantum mechanics. And this is precisely where our intuitive picture of the photon as a tiny ball starts to fall apart completely. Because when you think of something as a particle, your brain automatically assigns it a size, a shape, a definite location. But a photon doesn't work like that. A photon is not a tiny marble of light. When physicists say a photon is a particle, they don't mean the same thing you mean when you say a marble is a particle. They mean something much stranger, something that requires us to rethink what a particle even is. Here's the thing most people never get told. A photon is not really a thing sitting in space. A photon is an excitation of the electromagnetic field. That sounds abstract, so let me explain what it means. Imagine a calm lake on a windless day. The surface of the water is flat. Now imagine you drop a stone into the lake. A ripple appears. It spreads outward across the surface. The ripple is real. You can see it. You can measure its height, its speed, its wavelength. But here's the question. Is the ripple a thing? Or is it a disturbance in the water? You can't separate the ripple from the water. The ripple isn't an object sitting on top of the water. It is the water, moving in a particular way. If you somehow removed all the water, the ripple wouldn't exist anymore. It's a pattern, a behavior, a disturbance in something else. This is closer to what a photon actually is. The electromagnetic field is like the water. It fills all of space. It's everywhere. In the room you're sitting in right now, in the vacuum between the stars, in the space between atoms, and a photon is a ripple in that field. It's a disturbance and excitation, a specific pattern of oscillation in the electromagnetic field. The photon isn't sitting inside the field like a ball sitting in a bowl. The photon is the field doing something. It's the field vibrating in a quantized way with a specific amount of energy, a specific frequency, and a specific momentum. This is a radically different picture from the tiny glowing ball. There's no surface. There's no edge. There's no boundary where the photon stops and empty space begins. The photon is a quantum of the field itself. It's the minimum possible excitation of the electromagnetic field at a given frequency. You can't have half a photon. You can't have 3/4 of a photon. You can have 1 photon or 2 photons or 0 photons, but the field vibrates in whole units. These whole units are photons. Think of a guitar string. When the string is still, nothing is happening. But pluck the string and it vibrates. It produces a note with a specific pitch, corresponding to the frequency of vibration. In quantum mechanics, the energy of that vibrating string doesn't change smoothly and continuously. It changes in discrete steps. Each unit of vibrational energy is called a quantum. For the electromagnetic field, each quantum of vibration is a photon. The photon is the note the field is playing. It's not a thing attached to the field. It is the field in a state of excitation. This is why physicists almost never talk about a photon size in the way you talk about the size of a baseball or even the size of an atom. The question doesn't quite apply. What would the size of a ripple be? You could measure the wavelength of the ripple, the distance from one peak to the next. You could measure how spread out it is across the surface of the lake. But none of these are the size of the ripple in the way that the diameter of a baseball is the size of a baseball. The baseball has a definite boundary. The ripple doesn't. It fades gradually at the edges. Its spatial extent depends on how it was created and how it's been traveling. The same is true for photons. A photon's spatial character depends on the circumstances. It depends on its wavelength. It depends on how it was produced. It depends on what you're trying to measure and how you're trying to measure it. There is no single fixed number you can point to and say, that's how big a photon is. This is deeply uncomfortable for most people. We're used to a world where things have sizes. The Earth has a diameter of about 12,742 kilometers. An atom has a diameter of roughly 1/10 billionth of a meter. Even an electron, tiny as it is, has a classical radius that physicists sometimes refer to, about 2.8 times 10 to the negative 15 meters. Though that number comes with enormous caveats about what it actually means. But a photon? A photon doesn't have a classical radius. It doesn't have a diameter in the standard sense. It's not a ball. It's an excitation of a field. And the field doesn't have edges. Now, you might wonder how this works when you actually detect a photon. If a photon hits your eye, or hits a sensor, or lands on a photographic plate, it seems to arrive at a specific point. When scientists detect individual photons, they find them at definite locations. Doesn't that mean it has a definite position? This is one of the deepest puzzles in quantum mechanics. Before a photon is detected, it doesn't have a definite location. It's not hiding somewhere specific, waiting to be found. The photon's position is described by a probability distribution, a mathematical function that tells you the likelihood of finding the photon in any given place if you were to look. But until you actually detect the photon, the question where is it simply doesn't have a definite answer. The moment you detect it, the photon appears at a specific point. But this is the act of detection collapsing the probability into a single outcome. Before that moment, the photon was, in a very real sense, spread out. Not spread out like butter on toast, where you can point to the edges. Spread out like a wave on a pond, where the disturbance is more intense in some regions and less intense in others, but there's no hard line marking where it ends. This is what makes the photon so different from the objects we deal with in everyday life. A tennis ball has a surface. You can draw a line around it. Everything inside the line is tennis ball. Everything outside is not. A photon has no such line. A photon is a quantum of field excitation. Its spatial properties are described by wave functions and probability amplitudes, not by edges and surfaces. And this means the question how big is a photon is fundamentally different from the question how big is a tennis ball. It's not that we lack a precise enough ruler. It's that the concept of size as we normally understand it doesn't straightforwardly apply. When you hear the word particle in physics, especially in quantum physics, you need to mentally separate it from the word particle as you use it in everyday conversation. In everyday conversation, a particle is a small solid thing. In physics, a particle is a quantum excitation of a field. It's a unit of energy and momentum in a specific field mode. These are very different things that happen to share the same name. And this shared name causes enormous confusion. When physicists say a photon is a particle, they're saying it's a discrete, countable quantum of electromagnetic field energy. They come in whole units. That's what makes them particle-like. But they don't have surfaces or edges or fixed sizes. So the picture you should be building in your mind is not a tiny ball flying through space. Instead, imagine the electromagnetic field filling all of space like an invisible ocean. Most of the time, this ocean is calm. The field is in its ground state, its lowest energy configuration. A photon is a wave on this ocean. One single, indivisible wave packet with a specific energy and a specific frequency. You can't split it in half. It's one quantum, but its spatial extent, how spread out the wave is, depends on circumstances, and it doesn't have a hard edge. Classical physics treats the electromagnetic field as smooth and continuous. The field can have any energy it wants, but quantum mechanics reveals that the field is quantized. Its energy comes in discrete steps. The minimum step, the smallest possible amount of electromagnetic energy at a given frequency, is 1 photon. Below that, there's nothing but the vacuum, the ground state of the field. This ground state isn't truly empty. Even in what we call a vacuum, the electromagnetic field has fluctuations. These vacuum fluctuations are tiny, random oscillations that arise from quantum uncertainty. They've been measured experimentally through effects like the Casimir effect, where two closely spaced metal plates experience a measurable force because of vacuum fluctuations between them. A photon is 1 quantum above this background. It's the smallest possible excitation of the field above its ground state. It's not something placed into empty space. It's the field itself vibrating with 1 unit of energy at a particular frequency. Now think about what all this means for the idea of a photon size. You started with a simple mental picture. A tiny glowing ball, smaller than an atom, flying through space at the speed of light. But that picture is almost entirely wrong. A photon doesn't have a fixed size in the way a ball does. It's a quantum excitation of a field that fills all of space. Its spatial properties depend on its wavelength, on how it was created, on how it's being measured, and on the fundamental limits imposed by quantum mechanics. It interacts with matter at specific points, but before that interaction, it doesn't occupy a specific point. It exists as a probability distribution spread across space, sometimes tightly localized, sometimes spread out enormously. And here's the remarkable thing. Despite all this strangeness, despite the fact that we can't point to a photon and say it's this many nanometers wide, photons are among the most precisely understood objects in all of physics. Quantum electrodynamics, the theory that describes how photons interact with charged particles, is the most accurately tested theory in the history of science. Its predictions match experimental measurements to more than 10 decimal places. We understand photons better than we understand almost anything else in the natural world. We just can't give them a simple size. That gap between understanding and visualization is where the real story lies. We know exactly how photons behave. We can predict what they'll do in virtually any situation. But we cannot picture them in the straightforward way we picture a ball or a grain of sand. They're too quantum for that. Too wave-like and too particle-like at the same time. Too embedded in the fabric of the electromagnetic field to be pulled out and examined as separate little objects. And this is only the beginning. Because even though a photon doesn't have a size in the ordinary sense, it does have properties that give it a kind of spatial scale. The most important of these is its wavelength. And when you start looking at the wavelengths of different kinds of photons, when you compare radio wave photons to gamma ray photons, you discover something that stretches the concept of scale to its absolute limits. The range of wavelengths that photons can have spans more than 20 orders of magnitude, from waves longer than the diameter of a planet to oscillations smaller than an atomic nucleus. And all of them, every single one, is 1 photon, 1 quantum of the electromagnetic field. So if a photon isn't a tiny ball with a measurable diameter, if it's a quantum excitation of the electromagnetic field, rather than a little glowing marble flying through space, then how do we describe its scale at all? How do we assign any kind of spatial character to something that doesn't have edges or surfaces? The answer lies in a property that every photon possesses, a property so fundamental that it determines almost everything about how a photon behaves and what it can do. That property is its wavelength. And when you truly understand what wavelength means for a photon, when you see the staggering range of wavelengths that photons can have, you begin to grasp something extraordinary about the nature of light itself. But you also begin to see why wavelength is not the same thing as size, even though it's the closest thing to a spatial scale that a photon has. Let's start with what wavelength actually means. Remember the picture we built earlier? The electromagnetic field fills all of space. A photon is a vibration in that field, a single quantum of oscillation. The field oscillates up and down, cycling between peaks and troughs as the disturbance moves through space. The wavelength is the distance from one peak to the next. It's the spatial period of the oscillation. If the field oscillates slowly, the peaks are far apart and the wavelength is long. If the field oscillates rapidly, the peaks are close together and the wavelength is short. Now, here's where things become fascinating. Because the wavelengths that photons can have don't cluster around some single typical value. They span an absolutely enormous range. The electromagnetic spectrum, which is just the full catalogue of all possible photon wavelengths, stretches from waves that are longer than entire cities to oscillations that are smaller than the nucleus of an atom. And every single wavelength in that spectrum corresponds to a real kind of light that exists in nature, that can be produced, that can be detected, and that interacts with matter in its own distinctive way. Let's walk through this spectrum, starting from the longest wavelengths. At the long end, we have radio waves. Radio wave photons have wavelengths that can stretch from about a millimeter all the way up to hundreds of kilometers and beyond. AM radio signals have wavelengths of roughly a few hundred meters. FM radio signals have wavelengths of about 2 to 3 meters. Think about that for a moment. A single photon, one quantum of the electromagnetic field, one indivisible unit of light, can have a wavelength longer than a football field. These radio wave photons are all around you right now. They're passing through the walls of whatever room you're sitting in. They're passing through your body. Radio transmitters, cell towers, Wi-Fi routers, all of these devices produce photons with wavelengths ranging from centimeters to meters. Moving to shorter wavelengths, we hit microwaves. Microwave photons have wavelengths from about a millimeter to about 30 centimeters. The microwave oven in your kitchen produces photons with a wavelength of about 12 centimeters. These photons excite water molecules in your food, causing them to vibrate and heat up. The cosmic microwave background radiation, the faint glow left over from the early universe, consists of photons with wavelengths of about 1 to 2 millimeters. These ancient photons have been traveling through space for about 13.8 billion years. They started as extremely energetic gamma-ray photons in the blisteringly hot early universe, but the expansion of space has stretched their wavelengths enormously. They've been traveling so long that the universe itself has changed their scale. Next comes infrared radiation, with wavelengths from about 700 nanometers to about 1 millimeter. Everything that has a temperature above absolute zero emits infrared radiation. Your body emits infrared photons constantly. The heat you feel from a fire, from the sun on your skin, from a warm cup of coffee, that heat reaches you carried by infrared photons. Night vision goggles work by detecting these photons, essentially seeing the heat that objects emit, and then we reach visible light. This is the narrow sliver of the electromagnetic spectrum that human eyes can detect. Visible light photons have wavelengths from about 380 nanometers to about 700 nanometers. If the entire electromagnetic spectrum were a piano keyboard stretching from one end of a concert hall to the other, visible light would occupy less than a single key. But let me try another comparison, because the piano analogy still doesn't capture how absurdly narrow this sliver really is. Imagine a book with 1,000 pages. Each page represents a portion of the electromagnetic spectrum. The entirety of visible light, every color you've ever seen, every sunset, every rainbow, every painting, every face, every landscape, all the visual beauty the world has ever shown you would occupy a fraction of a single page in that 1,000-page book. Less than a page out of 1,000. That's how much of the electromagnetic spectrum your eyes can detect. The rest, the other 999 plus pages, is invisible to you. It's all around you, passing through you, filling the room, but you can't see any of it. You're essentially blind to 99.9% of the light in the universe. Red light sits at about 620 to 700 nanometers. Violet, the shortest wavelength visible to the human eye, is about 380 to 450 nanometers. Every color you've ever seen comes from photons in this incredibly narrow range. The entire visible world is generated by electromagnetic oscillations spanning a range of just about 320 nanometers. A range so narrow, it would be invisible on any chart of the full electromagnetic spectrum. Beyond violet, wavelengths get shorter and energies get higher. Ultraviolet light has wavelengths from about 10 nanometers to about 380 nanometers. These photons carry enough energy to damage biological molecules. Ultraviolet radiation from the sun is what causes sunburn. It can break chemical bonds in your DNA, which is why excessive UV exposure can cause skin cancer. Earth's ozone layer absorbs most of the sun's ultraviolet radiation, which is why the depletion of the ozone layer was such a serious concern. Shorter still are X-rays, with wavelengths from about 0.01 nanometers to about 10 nanometers. X-ray photons are energetic enough to pass through soft tissue, but are absorbed by denser materials like bone. X-ray wavelengths are roughly the same size as individual atoms, which is why X-ray crystallography can reveal the structure of molecules. When X-rays pass through a crystal, they diffract off the regularly spaced atoms, creating a pattern that scientists can analyze to determine where each atom is. This technique is how we figured out the structure of DNA. Rosalind Franklin's famous X-ray diffraction image of DNA, taken in 1952, showed a distinctive X-shaped pattern that revealed DNA's double helix structure. The photons she used had wavelengths comparable to the spacing between atoms in the molecule, which is precisely why they could resolve that structure. And finally, at the very short end of the spectrum, we have gamma rays. Gamma ray photons have wavelengths shorter than about 0.01 nanometers. The shortest gamma rays have wavelengths smaller than an atomic nucleus. The nucleus of a hydrogen atom, a single proton, has a diameter of about 1.7 times 10 to the negative 15 meters. Some gamma ray photons have wavelengths even shorter than this. These photons carry enormous amounts of energy. They're produced in the most violent events in the universe: nuclear explosions, supernova explosions, the decay of radioactive materials, the annihilation of matter and antimatter, gamma ray bursts, the most energetic explosions in the cool universe after the Big Bang itself, produce floods of gamma-ray photons that can briefly outshine entire galaxies. Now, stop and think about what we've just described. At one end of the spectrum, a single photon has a wavelength that can stretch for hundreds of meters or even kilometers. At the other end, a single photon has a wavelength smaller than an atomic nucleus. The ratio between these extremes is more than 20 orders of magnitude. That's a factor of 1 followed by 20 zeros. To put that in perspective, the ratio between the size of a single atom and the diameter of the entire Earth is only about 17 orders of magnitude. The range of photon wavelengths spans a larger ratio than the range from one atom to our entire planet. No other single physical property of any one type of particle spans such an enormous range of scales in nature. And yet, in every case, we're talking about one photon, one quantum of the electromagnetic field, one indivisible unit of light. This is where we need to be very careful about language, because it's tempting to conclude that the wavelength is the size of the photon. A radio wave photon is 100 meters wide. A gamma-ray photon is smaller than a nucleus. Simple. But that's not quite right. And understanding why is crucial to understanding the true scale of a photon. The wavelength tells you the spatial period of the electromagnetic field's oscillation. But the photon is not one wavelength long. The relationship between a photon and its wavelength is more subtle than that. Think back to the ripple on the lake. The ripple has a wavelength, the distance from one crest to the next. But the ripple itself might extend across many wavelengths. It might be a broad disturbance covering a large area, or a sharp splash covering a very short distance. In both cases, the wavelength is the same, but the spatial extent is completely different. The wavelength tells you the character of the oscillation, but it doesn't tell you how far the disturbance extends. For photons, the same principle applies. A photon emitted by an atom during an energy level transition might be a fairly well localized wave packet, extending over maybe a few meters. A photon in a laser beam might extend over much greater distances, because lasers produce highly coherent light with very well-defined frequencies. The spatial extent of a photon is not the same as its wavelength. The two are related, but they're not the same thing, and yet, the wavelength is the most important spatial scale associated with a photon. It determines how the photon interacts with the physical world, not as a measure of the photon's physical extent, but as a measure of what the photon can do. This is because of a fundamental principle in wave physics. A wave can only interact strongly with structures that are comparable in size to its wavelength. Structures much larger than the wavelength see the wave as a smooth, featureless field. Structures much smaller than the wavelength are essentially invisible to the wave. Only structures that are roughly the same size as the wavelength interact strongly with the wave. This principle explains an enormous amount about how different kinds of light behave. Radio waves have wavelengths of meters to kilometers. They pass right through walls, through buildings, through human bodies. That's why your radio works indoors. The walls are small compared to the wavelength, so they barely interact with the wave. Visible light has wavelengths of a few hundred nanometers, roughly the scale of molecular structures and small particles. That's why you can see dust motes floating in a sunbeam, and that's why the sky is blue. Molecules in Earth's atmosphere scatter light, and the scattering is more efficient for shorter wavelengths. Blue photons get deflected in all directions, filling the sky with blue light while the red photons pass through more directly. At sunset, sunlight travels through more atmosphere, scattering away most of the blue light, which is why sunsets are red. X-rays have wavelengths comparable to atomic spacings. This is why they can reveal crystal structures and molecular arrangements. Gamma rays have wavelengths comparable to or smaller than nuclear dimensions. This is why they can probe the structure of atomic nuclei. So, the wavelength of a photon determines its relationship with the physical world. But here's the critical distinction. The wavelength determines how a photon interacts with matter. It does not define the physical boundary of the photon itself. A radio wave photon with a wavelength of 100 meters does not mean there's a physical object 100 meters wide flying through space. The wavelength is the scale of the field's oscillation. If you think of the photon as a note played on the electromagnetic field, the wavelength is the pitch of the note. But the pitch doesn't tell you how big the note is. It tells you the character of the vibration. This distinction matters enormously because without it, you end up with absurd conclusions. If wavelength were the same as size, then a radio wave photon would be hundreds of meters across. And yet, you can absorb a single radio wave photon with a single atom under the right conditions. The photon's wavelength is enormous, but it can be absorbed by something much smaller than that wavelength. How can something hundreds of meters wide be absorbed by something smaller than a billionth of a meter? The answer is that the wavelength isn't the photon's size. It's the scale of the field's oscillation. The photon itself, as a quantum of energy, can be absorbed whenever it encounters a system capable of absorbing that particular quantum of energy. The spatial extent of the absorption event doesn't have to match the wavelength. Let me give you another example that makes this even clearer. Think about a radio antenna on your car. The antenna might be half a meter long. The FM radio signal it's picking up has a wavelength of about 3 meters. The antenna is much shorter than the wavelength, and yet it absorbs the photon's energy. It doesn't need to be 3 meters long. It just needs to be capable of resonating with the electromagnetic oscillation at that frequency. The antenna works not because it matches the photon's size, but because it matches the photon's frequency. The wavelength and the size of the absorber are different things entirely. Conversely, a gamma ray photon with a wavelength smaller than an atomic nucleus can still be detected by a detector that's centimeters across. The photon shows up somewhere in the detector. Its energy transferred to a single particle at a single point, but the detector can be vastly larger than the wavelength. The detector doesn't need to be nucleus-sized. It just needs to contain particles capable of absorbing that quantum of energy. There's another property intimately connected to wavelength that deepens this picture. Frequency. Wavelength and frequency are directly related. Their product always equals the speed of light. Long wavelength photons have low frequencies. Visible light photons oscillate hundreds of trillions of times per second. Gamma ray photons oscillate trillions of times per second. Frequency is important because it's directly connected to energy. Each photon's energy equals Planck's constant multiplied by its frequency. Higher frequency means higher energy. And since frequency and wavelength are inversely related, shorter wavelength also means higher energy. A gamma ray photon with a wavelength smaller than a nucleus carries an enormous amount of energy. A radio wave photon with a wavelength of 100 meters carries an almost inconceivably tiny amount of energy. How tiny? A single radio wave photon at 100 megahertz carries about 6.6 times 10 to the negative 26 joules of energy. A single visible light photon carries roughly 1,000,000 times more energy. And a single gamma-ray photon from a nuclear decay can carry billions of times more energy than a visible light photon. The energy range of photons is just as vast as the wavelength range. This connection between wavelength and energy has physical consequences, central to how the universe works. Infrared photons have just enough energy to make molecules vibrate, which is why they produce heat. Visible light photons have enough energy to excite electrons and atoms to higher energy levels, which is why they can trigger chemical reactions in your retina, allowing you to see. Ultraviolet photons have enough energy to break certain chemical bonds. X-ray photons have enough energy to knock inner electrons out of atoms entirely. Gamma-ray photons have enough energy to penetrate atomic nuclei and even create new particles. This relationship between wavelength and energy also explains something you encounter every single day but probably never think about in terms of photons. Why plants are green? Sunlight contains photons across the visible spectrum. When sunlight hits a leaf, the chlorophyll molecules inside absorb red and blue photons because those photons carry the right amounts of energy to drive photosynthesis. Red photons have just enough energy to kickstart the chemical reactions that convert carbon dioxide and water into sugar and oxygen. Blue photons actually carry a bit more energy than needed, and the excess gets dissipated as heat. But green photons sit in the middle. They carry an amount of energy that doesn't quite match what chlorophyll needs. So the leaf reflects them. And those reflected green photons travel from the leaf to your eye, which is why the leaf looks green. The color of every plant on Earth is determined by which photon wavelengths carry the right quantum of energy for photosynthesis, and which ones don't. The greenness of a forest is a direct consequence of Planck's relationship between energy and frequency. Solar cells work on a similar principle. A solar panel is made of semiconductor material, usually silicon. When a photon hits the silicon, it can knock an electron loose from its atom if, and only if, the photon carries enough energy. For silicon, the minimum energy needed corresponds to a wavelength of about 1,100 nanometers, which is in the near-infrared. Photons with wavelengths shorter than this, which means higher energy photons, can free electrons and generate electricity. Photons with longer wavelengths don't carry enough energy. They pass through the silicon or just warm it up. This is why solar panels can't convert all sunlight into electricity. A large portion of the sun's photons either carry too little energy to free electrons or carry so much energy that the excess is wasted as heat. The theoretical maximum efficiency of a single junction silicon solar cell is about 33%, and the limit is set entirely by the relationship between photon wavelength and energy. The wavelength is the spatial face of this energy. Short wavelength, high energy, able to interact with small dense structures. Long wavelength, low energy, interacting with large structures or passing right through small ones. So, where does all this leave us? A photon doesn't have a size in the classical sense, but it does have a wavelength, a spatial scale that characterizes its oscillation and determines how it interacts with the world. This wavelength ranges from kilometers to less than the width of an atomic nucleus, a span of more than 20 orders of magnitude. But the wavelength is not the size of the photon. It's the scale of the field's oscillation. A photon with a wavelength of 100 meters is not a sphere 100 meters across. A photon with a wavelength of 1 femtometer is not a tiny dot 1 femtometer wide. The wavelength describes the pattern of the oscillation, not the physical extent of the photon as an object. There's something almost poetic about this. The most visible thing in the universe, light itself, the medium through which we perceive everything, refuses to be pinned down to a definite spatial scale. It has wavelength, and that wavelength matters enormously. It determines the color we see, the structures we can probe, the technologies we can build. But it's not a size, not in the way we normally mean. It's something stranger and more beautiful. A spatial signature of energy, a rhythmic pattern in the fabric of reality, stretching from the cosmic to the subatomic in a single unbroken spectrum. And we still haven't gotten to the deepest part of this puzzle. Because beyond wavelength, beyond frequency, there's another layer to the photon's spatial character, a layer governed by the fundamental rules of quantum mechanics itself. The rules that determine where a photon can be found when you actually try to look for it. And those rules make the question of the photon's true scale stranger, and more fascinating than anything we've discussed so far. We've established that a photon has a wavelength, and that this wavelength spans an almost unimaginable range across the electromagnetic spectrum. But we've also seen that wavelength isn't really the photon's size. So the question remains, if wavelength doesn't give us the photon's size, is there anything that does? Can we at least say where a photon is? This is where we enter the deepest and strangest territory in all of physics. Because quantum mechanics doesn't just make it difficult to locate a photon, it makes it fundamentally, absolutely, inescapably impossible to assign a photon a precise position and a precise momentum at the same time. And this isn't a limitation of our instruments. It's a law of nature, built into the structure of reality itself. Let's start with the connection between wavelength and energy, because this relationship is the key that unlocks the rest. Every photon's energy is determined by its frequency. Energy equals Planck's constant times frequency. Since frequency and wavelength are inversely related, you can also express this as energy equals Planck's constant times the speed of light divided by the wavelength. Shorter wavelength means higher energy. Longer wavelength means lower energy. A gamma ray photon with a wavelength of 1 picometer carries about 2 × 10 to the negative 13 joules of energy. That's enough energy to knock electrons out of atoms, to break molecular bonds, to penetrate deep into matter. Meanwhile, a radio wave photon at a frequency of 1 megahertz carries about 6.6 × 10 to the negative 28 joules. That's roughly a quadrillion times less energy. It's such a tiny amount that detecting a single radio wave photon is extraordinarily difficult. Radio telescopes don't detect individual photons the way your eye detects visible light photons. They detect the combined electromagnetic field from enormous numbers of photons arriving simultaneously. But here's where things take an unexpected turn. This connection between energy and wavelength doesn't just determine how photons interact with the world around them. It also determines how precisely we can know where a photon is. This brings us to the Heisenberg uncertainty principle, named after Werner Heisenberg, who formulated it in 1927. This principle states that there is a fundamental limit to how precisely you can simultaneously know certain pairs of physical properties of any quantum particle. The most famous pair is position and momentum. You cannot know both the exact position and the exact momentum of a particle at the same time. The more precisely you know one, the less precisely you can know the other. This is not about the quality of your instruments. It's a fundamental property of nature. For a photon, this takes on a particularly dramatic form. The momentum of a photon is directly related to its wavelength. So if you know a photon's wavelength very precisely, you know its momentum very precisely. But the uncertainty principle then tells you that the photon's position must be highly uncertain. Conversely, if you try to localize a photon very precisely, its momentum becomes highly uncertain. And since momentum is related to wavelength, its wavelength and energy also become uncertain. Imagine a photon with a very well-defined wavelength. Say a green photon with a wavelength of exactly 550 nanometers. The photon's momentum is extremely well known, but that means the photon's position is extremely poorly defined. It could be essentially anywhere along its direction of travel. Now imagine the opposite. You try to confine a photon to a very small region of space. As you squeeze the photon's position into a smaller and smaller region, its wavelength stops being well defined. Instead, the photon's wave function becomes a superposition of many different wavelengths. This is because a wave that's localized to a small region can't be a perfect single wavelength oscillation. A perfect single wavelength wave extends forever in both directions. That's the only way to have a perfectly defined wavelength. But that wave is everywhere. To create a localized wave, you have to add together many different wavelengths. This is one of the most important ideas in all of wave physics, and it's worth taking a moment to really understand it because it's the key to understanding why a photon can't have both a definite position and a definite wavelength. Think of a pure musical tone. A single perfect note, like a tuning fork produces. That note is a wave with one single frequency. If you could see this wave stretched out in space, it would be a perfectly regular oscillation extending in both directions without end. Peak, trough, on and on forever. Its wavelength is perfectly defined. You can measure the distance from one peak to the next, and it's always exactly the same. But the wave is everywhere. It has no localization at all. It extends to infinity. You can't point to any spot and say, the wave is here and not there. It's everywhere equally. Now, imagine you want to create a wave that's concentrated in one spot. A pulse, a burst, something that exists here and not over there. To do that, you can't use a single wavelength. You need to combine many different wavelengths. When waves of different wavelengths overlap, something interesting happens. In some regions, the peaks of different waves line up and reinforce each other, creating a strong combined signal. In other regions, the peaks and troughs of different waves are out of sync, and they cancel each other out, creating silence. The result is what physicists call a wave packet. A concentrated burst of wave activity in one region surrounded by quiet on either side. The more wavelengths you add, the tighter you can make this packet. If you combine just a few wavelengths, the packet is broad and fuzzy. If you combine thousands of wavelengths, you can make it very tight, very localized. But here's the price you pay. The wave packet no longer has a single well-defined wavelength. It's a mixture, a blend, a superposition of many different wavelengths all added together. And each of those wavelengths corresponds to a different momentum and a different energy. So the more localized you make the packet, the more uncertain the wavelength becomes, and with it the momentum and the energy. This is the uncertainty principle in action. It's not just an abstract mathematical rule, It arises directly from the wave nature of quantum objects. Localization requires a spread of wavelengths. A spread of wavelengths means uncertain momentum. Precise momentum requires a single wavelength. A single wavelength means total delocalization. You can't escape this trade-off. It's built into the mathematics of waves themselves. One of the most powerful demonstrations of this behavior is the double-slit experiment performed with individual photons. You set up a barrier with two narrow slits and a sensitive detector behind it, then send photons through one at a time. The first photon hits the detector at some seemingly random location. The second hits somewhere else. At first, the pattern looks random, but as you accumulate thousands of detections, the dots arrange themselves into an interference pattern. The exact same pattern that Young observed with an intense beam of light. Each photon went through the apparatus alone. There was no other photon to interfere with, and yet, the interference pattern emerged. Each individual photon somehow interfered with itself. Each photon went through both slits simultaneously, existing as a superposition in which both paths were taken at the same time. And when the photon was finally detected, it appeared at one specific point. But where exactly any individual photon would land was fundamentally unpredictable. As the photon passes through the two slits, where is it? The answer from quantum mechanics is that the question doesn't have a meaningful answer. The photon doesn't have a definite location. It exists in a superposition of being at both slits simultaneously. If you try to determine which slit the photon went through by placing a detector at one of the slits, the interference pattern disappears. The act of measuring which slit the photon passes through forces it to have a definite location. And once it has a definite location at one slit, it can't interfere with itself from the other. By trying to find out where the photon is, you change what it does. This is the essence of the measurement problem in quantum mechanics. Before you measure, the photon doesn't have a definite position. When you measure, the wave function collapses to a single point. The photon appears somewhere specific, but you couldn't have predicted exactly where. What does this mean for the photon's scale? It means that asking how big is a photon is complicated in yet another way. The photon doesn't even have a definite spatial extent before you measure it. Its position is fundamentally indefinite. And any attempt to make its position more precise automatically makes other properties like its energy and momentum less precise. This leads to genuine physical consequences. One of the most striking is the energy-time uncertainty relation. It states that the uncertainty in a photon's energy multiplied by the uncertainty in the time at which it's detected must always be greater than or equal to Planck's constant divided by 4 pi. Ultra-fast laser pulses demonstrate this beautifully. A laser can produce an extremely short pulse lasting only a few femtoseconds. These pulses are incredibly well localized in time. But because of the energy-time uncertainty relation, such a short pulse cannot have a single well-defined wavelength. It must contain a spread of wavelengths, a range of colors. The shorter the pulse, the broader the range of wavelengths it contains. This isn't just a theoretical curiosity. It has practical consequences in real technology. Ultra-fast lasers are used in eye surgery, in machining microcomponents for electronics, and in studying chemical reactions that happen in trillionths of a second. In every case, the engineers building these systems have to account for the fact that a shorter pulse means a broader range of wavelengths. You can't have a perfectly sharp pulse of perfectly pure color. The universe doesn't allow it. If your laser pulse lasts 10 femtoseconds, it necessarily contains a spread of wavelengths spanning tens of nanometers. This affects how tightly you can focus the beam, how precisely you can target a particular chemical bond, and how much energy gets deposited in the material you're working on. The uncertainty principle isn't an abstract philosophical idea. It's a design constraint that engineers deal with every day. Now, let's talk about what happens when you try to use photons to measure the size of very small things. This is where the photon's behavior under the uncertainty principle becomes not just theoretically interesting, but practically urgent. Suppose you want to measure the position of an atom. You shine light on it and observe how the light scatters. But there's a limit to how small a feature you can see with light. This limit is set by the wavelength. You cannot resolve features smaller than roughly half the wavelength. This is called the diffraction limit. With visible light, the smallest features you can resolve are about 200 nanometers. This limit was first identified rigorously in the 1870s by Ernst Abbe, a German physicist working with the Zeiss optical company. Abbe showed that no matter how perfectly you grind your lenses, no matter how flawless your optical system, you cannot see anything smaller than roughly half the wavelength of the light you're using. This was devastating for biologists. Cells are typically 10 to 100 micrometers across, which is well within the range of visible light microscopes. But the structures inside cells, the organelles, the protein complexes, the molecular machinery that makes life work, many of these are smaller than 200 nanometers. They're beyond the diffraction limit. For over a century, biologists could see cells but couldn't see what was happening inside them in fine detail. The photon's wavelength set a hard wall on what could be observed. In 2014, the Nobel Prize in Chemistry was awarded to Eric Betzig, Stefan Hell, and William Warner for developing super-resolution microscopy techniques that found clever ways to partially circumvent Abbe's limit. These techniques don't actually violate the diffraction limit. They work around it by exploiting the quantum behavior of individual fluorescent molecules. By switching molecules on and off one at a time and recording each one's position with high precision, they can build up an image with resolution far below 200 nanometers. Some modern techniques achieve resolution of 20 or 30 nanometers, nearly 10 times better than the classical limit. But even these techniques ultimately depend on the photon's wavelength. They're still using visible light photons. They've just found ingenious ways to extract more spatial information from how those photons interact with individual molecules. The diffraction limit isn't broken. It's outsmarted. And the very need to outsmart it demonstrates how fundamentally the photon's wavelength constrains what we can see. To see even smaller things, you need shorter wavelengths, and shorter wavelength means higher energy. When you shine X-rays on a molecule, each photon carries much more energy, and when that energetic photon scatters off the molecule, it can disturb it, knock electrons out, break bonds, even destroy it. The more precisely you try to measure something's position, the more violently you disturb it. This is the uncertainty principle in action. This creates a genuine dilemma for scientists. In structural biology, researchers want to see the shapes of proteins and other molecules at atomic resolution. To do that, they need X-ray photons with wavelengths comparable to the spacing between atoms, about 1 to 2/10 of a nanometer. But those X-ray photons carry enough energy to damage the very molecules they're trying to image. In traditional X-ray crystallography, this is managed by using crystals, millions of copies of the same molecule arranged in a regular lattice. The X-rays damage individual molecules, but because there are millions of identical copies, you can average the signal and still get a clear picture. But if you only have one copy of the molecule, one single protein floating in solution, you can't do that. The X-ray photon that reveals the molecule's shape also destroys the molecule. Recent advances with X-ray free electron lasers have found a way around this. These facilities produce incredibly intense, incredibly short pulses of X-rays. The pulse hits the molecule and diffracts before the molecule has time to explode. The photons scatter off the atoms and create a diffraction pattern in the detector. And then, a fraction of a femtosecond later, the molecule is destroyed by the energy the photons deposited. But by then, these scattered photons have already carried the structural information to the detector. You literally take the picture faster than the molecule can blow apart. This technique, called serial femtosecond crystallography, is one of the most stunning examples of the uncertainty principle playing out in real experimental science. You can't observe without disturbing, but if you're fast enough, you can capture the information before the disturbance matters. There's a fascinating thought experiment that takes this principle to its logical extreme. Imagine trying to trap a photon in a box with perfectly reflecting walls. The photon bounces back and forth between the walls forever, confined to the interior. The photon is localized. You know it's inside the box, but the smaller you make the box, the more uncertain the photon's momentum becomes. Let's walk through this step by step. Start with a box the size of a room, about 3 meters across. A visible light photon inside this box has plenty of space. Its momentum uncertainty is small. Its energy is close to what you'd expect for a photon of that wavelength. Everything seems normal. Now shrink the box to 1 centimeter. The photon is more confined. The uncertainty principle forces a larger spread in its possible momenta, which means a larger spread in its possible wavelengths. The photon no longer has a single, well-defined wavelength. It's a superposition of many wavelengths. Its minimum energy has increased because you can't confine a wave to a small space without the wave having at least some short wavelength components, and short wavelength means high energy. Shrink the box further to 1 nanometer, about the width of a few atoms. Now the momentum uncertainty is enormous. The photon's energy has skyrocketed. At this scale, the minimum energy of the confined photon is in the range of hundreds of electron volts. That's X-ray territory. You start with a visible light photon, but by squeezing it into a tiny space, you've turned it into something with the energy of an X-ray. The act of confining the photon has changed its fundamental character. And if you try to go even smaller, shrinking the box to nuclear dimensions, about 1 femtometer, the energy required becomes so astronomical that it would be enough to create electron-positron pairs out of the vacuum. The photon's confinement energy exceeds twice the rest mass energy of an electron, about 1 million electron volts. At that point, the energy you've pumped into the system by confining the photon starts creating new particles. The universe responds to your attempt to localize the photon by generating matter. This is a genuine physical limit. The more you try to squeeze a photon into a small space, the more the universe pushes back, generating new physics that prevents you from localizing it further. This is fundamentally different from how ordinary objects behave. You can put a marble in a box of any size. The marble doesn't resist being confined. but a photon does. Every gain in spatial precision costs you something in energy precision. And at extreme confinement, the energy cost becomes so high that entirely new phenomena emerge. The photon refuses to be pinned down, not just passively by lacking a definite position, but actively, by requiring more and more energy the harder you try to confine it, until the energy itself creates new particles and the whole concept of confining a single photon breaks down. And this isn't just a thought experiment that lives on a blackboard. This physics is real. It connects to some of the deepest questions in modern physics about the nature of the vacuum itself. Remember how we talked earlier about the electromagnetic field's ground state, the vacuum not being truly empty? That even in empty space, the field has tiny quantum fluctuations? Those fluctuations are directly related to what happens when you try to confine a photon to a very small space. The vacuum, it turns out, is not a passive backdrop against which physics happens. It's an active participant. Quantum field theory tells us that the vacuum is constantly fizzing with what physicists call virtual particle pairs. Pairs of particles and antiparticles, like electrons and positrons, that briefly flicker into existence and then annihilate each other before they can be directly observed. These virtual pairs exist for incredibly short durations, allowed by the energy-time uncertainty relation. They borrow energy from the vacuum, exist for a fleeting moment, and then pay it back by disappearing. Under normal conditions, you can't see them. They're too brief, too faint, too ephemeral, but they're real. They have measurable effects. The Casimir effect, where two metal plates in a vacuum experience a force pushing them together, is caused by virtual particles. The Lamb shift, a tiny change in the energy levels of hydrogen atoms that was measured in 1947, is caused by virtual photons briefly popping into existence near the electron. These are real, measured phenomena that prove the vacuum is not empty. It's alive with quantum activity. When you try to confine a photon to a space smaller than about a femtometer, you're pumping so much energy into the system that the virtual particle pairs lurking in the vacuum can become real. The energy of confinement is large enough to pull virtual electron-positron pairs out of the vacuum and make them permanent. This is the same physics that operates near the event horizons of black holes. In the intense gravitational field near a black hole, the curvature of space-time is so extreme that virtual particle pairs can be torn apart before they have a chance to annihilate. One particle falls into the black hole, the other escapes into space as real radiation. This process, predicted by Stephen Hawking in 1974, is called Hawking radiation. It means that black holes aren't completely black. They slowly radiate energy and, over unimaginably long time scales, eventually evaporate. The connection between confining a photon and Hawking radiation might seem surprising. One is a thought experiment about a photon in a box. The other involves the most extreme objects in the universe. But the underlying physics is the same. In both cases, extreme confinement or extreme curvature of space-time makes the vacuum unstable. The vacuum's virtual particles become real. New matter is created from what appeared to be nothing. The photon's resistance to confinement isn't just a quirky feature of quantum mechanics. It's a window into the deeper structure of the vacuum itself, into the relationship between energy and matter, and into the fundamental instability that lurks beneath the apparent emptiness of space. When you try to pin down a photon's position too precisely, you're not just bumping up against the uncertainty principle. You're probing the boundary between light and matter, between the quantum field's ground state and its excited states, between the vacuum as we normally think of it and the seething quantum foam that reality is actually made of. Modern single photon detectors bring all of these abstract principles into physical reality. Avalanche photodiodes, superconducting nanowire detectors, and photomultiplier tubes can all detect single photons. When a single photon hits one of these detectors, an electron is knocked loose, triggering a cascade that produces a measurable electrical signal. The photon is absorbed. Its energy has been transferred to the detector, and the location is recorded. But decades of experiments have shown that if you repeat the experiment identically, the photon doesn't always appear at the same point. It appears at different points each time, following a probability distribution predicted by quantum mechanics. There is no hidden variable that determines in advance where the photon will land. The randomness is genuine. That last statement, that there is no hidden variable, is one of the most extraordinary claims in all of science. And it didn't go unchallenged. In fact, the greatest physicist of the 20th century spent decades arguing against it. Albert Einstein, the very man who proved the photons exist, refused to accept that their behavior was fundamentally random. He believed that quantum mechanics must be incomplete, that there had to be some deeper layer of reality, some hidden mechanism operating beneath the quantum level that determined exactly where each photon would go. The randomness, Einstein argued, was just our ignorance of this deeper mechanism. Quantum mechanics gave the right statistical predictions, but it wasn't the whole story. There had to be hidden variables. Einstein expressed this objection most famously in a 1935 paper co-authored with Boris Podolsky and Nathan Rosen. The paper, known as the EPR paradox, argued that quantum mechanics must be incomplete because it couldn't simultaneously assign definite values to certain properties of entangled particles. Einstein believed this proved that something was missing from the theory, some hidden information that quantum mechanics failed to capture. He reportedly told colleagues that he couldn't believe God plays dice with the universe. For decades, it seemed like the debate was purely philosophical. There was no way to experimentally distinguish between Einstein's view that hidden variables existed and the standard quantum mechanical view that the randomness was fundamental. Then, in 1964, a physicist named John Bell showed that there was a difference. Bell proved mathematically that if hidden variables existed, the results of certain experiments on entangled particles would have to satisfy specific statistical limits, now called Bell inequalities. Quantum mechanics predicted that these limits would be violated. If you could perform the right experiment, you could tell whether Einstein or quantum mechanics was right. In the early 1980s, Alain Aspect and his colleagues in Paris performed exactly this experiment. They created pairs of entangled photons and measured their properties at two separate detectors. With the measurement settings chosen randomly and so quickly that no signal traveling at the speed of light could communicate between the two detectors during the measurement. The results violated Bell's inequalities. Quantum mechanics was right. Einstein was wrong on this specific point. There are no hidden variables, at least not of the kind Einstein imagined. The randomness of photon detection is not our ignorance of some deeper clockwork. It is a feature of reality itself. There is nothing more to know. The photon genuinely does not have a definite position before it's measured, and the outcome of the measurement is genuinely irreducibly random, constrained only by the probabilities that quantum mechanics predicts. Aspect's work was so significant that he was awarded the Nobel Prize in Physics in 2022, alongside John Clauser and Anton Zeilinger, for experiments that settled one of the deepest debates in the history of physics. Let me bring all of this together. You ask, how big is a photon? And what you find is that every attempt to answer runs into a fundamental barrier. The photon has a wavelength, but the wavelength is the scale of the field's oscillation, not the size of a physical object. The photon can be detected at a specific point, but before detection, it doesn't occupy a specific point. If you try to localize it, its energy becomes uncertain. If you try to give it a precise wavelength, it becomes delocalized. You can't have both. The uncertainty principle ensures that there is always a trade-off between knowing where a photon is and knowing what kind of photon it is. And yet, this isn't a failure of physics. We understand photons extraordinarily well. Quantum electrodynamics predicts the behavior of photons with an accuracy unmatched by any other theory in the history of science. Our understanding is not lacking. What's lacking is the adequacy of our everyday concepts. The words and pictures and intuitions we've built from a lifetime of interacting with baseballs and marbles and grains of sand. Those concepts work beautifully for baseballs. They don't work for photons, and the failure isn't in the photon. It's in the concepts. The photon is telling us something profound about the nature of reality. It's telling us that, at the most fundamental level, the universe is not made of little solid objects with definite sizes sitting at definite locations. It's made of quantum fields, vibrating, fluctuating, existing in superpositions of states, obeying rules that are precise and beautiful, but utterly unlike anything in our daily experience. The photon is a messenger from this deeper reality. Every time you see light, every time a photon enters your eye and triggers a signal in your retina, you're receiving a message from the quantum world. And that message says the universe is stranger, more subtle, and more wonderful than you ever imagined. And now, having seen all the pieces, the wavelength that isn't really a size, the energy that reshapes what scale means, the uncertainty that forbids any clean spatial boundary, we're finally ready to pull everything together and confront the full picture of what the true scale of a photon really is. So here we are. We've spent this entire journey trying to answer what seemed like the simplest possible question. How big is a photon? And at every turn, the answer has slipped away from us. Not because we don't understand photons, we understand them extraordinarily well, but because the question itself assumes something that isn't true. It assumes that a photon is the kind of thing that has a size, a definite, fixed, measurable size, the way a marble has a diameter or a grain of sand has a width. And it's not. A photon is something else entirely. Something that demands a completely different way of thinking about what it means for something to occupy space. Let's pull all the threads together and see the full picture. We started with the most natural intuition in the world. You hear that light is made of particles, and your brain immediately pictures tiny, glowing balls. But we discovered that this picture is fundamentally wrong. A photon is not a little ball. It's a quantum excitation of the electromagnetic field, a ripple in a field that fills all of space. It doesn't have a surface or a boundary. Then we explored wavelength, spanning an almost inconceivable range. Radio wave photons oscillate with wavelengths stretching hundreds of meters. Gamma-ray photons have wavelengths smaller than atomic nuclei. The ratio exceeds 20 orders of magnitude. But wavelength isn't size. It describes the character of the vibration, not the extent of the thing vibrating. Then the uncertainty principle made the question impossible in the classical sense. A photon cannot simultaneously have a precise position and a precise wavelength. Every attempt to localize it more tightly costs you precision in its energy. The universe forbids any measurement that simultaneously reveals both where a photon is and what its wavelength is with unlimited precision. So there is no single number you can point to and say, that's how big a photon is. The photon's spatial character is contextual. It depends on what you're asking, how you're measuring, and what you've already determined about its other properties. This is not vagueness. This is the precise, mathematically rigorous, experimentally confirmed reality of quantum physics. Let's explore this contextual nature more carefully, because it reveals something genuinely profound about how the universe works. Consider a photon emitted by an atom. An electron drops from a higher energy level to a lower one, and the energy difference is carried away by a photon. This process takes about 10 nanoseconds. During that time, the photon is being emitted gradually, and the result is a wave packet extending over a finite region of space. For a typical optical photon, this wave packet is about 3 meters long. The photon is spread out over 3 meters along its direction of travel. That might seem surprising. 3 meters. That's the height of a room. A single photon from a light bulb occupies a space you could walk through. But remember, the photon is moving at the speed of light. It covers those 3 meters in about 10 billionths of a second. The wave packet's spatial length is just the emission time multiplied by the speed of light. And this length is the coherence length, the distance over which the photon's wave function maintains a definite phase relationship. Beyond that distance, the phase becomes random and the wave function fades. What does this wave packet actually look like? If you could somehow freeze time and see the electromagnetic field's excitation, you'd see an oscillating disturbance about 3 meters long. Inside those 3 meters, the field would be vibrating at the frequency of the photon, perhaps 500 trillion oscillations per second for green light. The amplitude would be strongest near the center of the packet and would fade toward the edges. There would be no sharp boundary. The oscillation would just get weaker and weaker until it disappeared in the background noise of vacuum fluctuations. This is not a ball. It's not a dot. It's a fuzzy, oscillating disturbance with no definite edges, stretching across a space you could reach out and touch if it weren't moving at 300,000 kilometers per second. Now consider a very different photon. A photon produced by a high-quality laser. Lasers produce light with an extremely well-defined frequency. A single-mode laser might have a frequency uncertainty of just a few kilohertz. Because the frequency is so precisely defined, the corresponding wave packet is enormously long. Using the uncertainty principle, a photon from such a laser can have a coherence length of tens or even hundreds of kilometers. The photon's wave function extends over vast distances. It's spread out across a region you could drive through in an hour, and yet it's still one photon, one quantum of light, one indivisible unit of electromagnetic energy. If you tried to split it with a beam splitter, you wouldn't get 2 half photons. You'd find one whole photon going one way and nothing going the other, or vice versa, with probabilities determined by the beam splitter's properties. The photon is 100 kilometers of coherent wave function and is still indivisible. Compare this to a photon from an ultra-fast laser pulse. These pulses can last just a few femtoseconds. During that time, light travels only about a micrometer. The photon is localized to an extremely short wave packet. If you could freeze it in place, you'd see just a few oscillations of the electromagnetic field, maybe 3 or 4 peaks and troughs, crammed into a space smaller than the width of a human hair. But because it's so well localized, its frequency is highly uncertain. It doesn't have a single well-defined wavelength. Instead, it contains a broad spread of wavelengths, spanning a wide range of colors. If this photon were in the visible range, it wouldn't be green or red or blue. It would be white, a mixture of all colors, because its wave function contains all those wavelengths simultaneously. Look at what we have. 3 photons, one from an atom spread over about 3 meters, one from a precision laser spread over tens of kilometers, one from an ultra-fast pulse confined to a few micrometers. All 3 are single photons. All 3 are one quantum of electromagnetic energy. But their spatial extents differ by factors of billions. There is no single answer to how big is a photon, because the answer depends entirely on how the photon was created and how precisely its frequency is defined. And we haven't even talked about the transverse spread, the extent of the photon perpendicular to its direction of travel. This is where things become almost surreal. A photon emitted by a distant star arrives at Earth with a wave function that's spread out across an enormous area. Consider Sirius, the brightest star in the night sky, about 8.6 light-years away. A photon emitted by Sirius travels for 8.6 years through the vacuum of space. During that journey, its wave function spreads out transversely. By the time it reaches Earth, the photon's probability distribution covers an area that might span the entire diameter of our planet. The photon might be detected by a telescope in Chile, or a telescope in Hawaii, or your naked eye standing in a field in Nebraska. Any detector on the night side of Earth that happens to be pointed in the right direction could catch this photon. Its transverse extent is essentially planetary, but the moment it's detected, when it hits a CCD pixel in a telescope or a rhodopsin molecule in your retina, it appears at a single point. The entire probability distribution, spread across thousands of kilometers, collapses to one location. All the probability that was distributed across the face of the Earth concentrates at one spot, in one molecule, in one eye. Think about what this means. One instant, the photon's wave function covers an area the size of a continent. The next instant, it's been absorbed by a single molecule about 1 nanometer across. The ratio between those two spatial scales is about 10 to the 15th power. A quadrillion to 1. All of that probability vanishing from everywhere else and appearing at one single point. This is not a simplification or a metaphor. This is genuinely what happens. When astronomers point a telescope at a distant star and detect individual photons one by one, each photon could in principle have been detected by any other telescope on the planet. The photon's wave function spread out over the entire wavefront that reached Earth. But each photon is only detected once, at one location, by one detector. The rest of the wavefront yields nothing. And there's something even stranger about this photon's journey that most people never consider. From the photon's own perspective, to the extent that phrase even makes sense, the journey didn't take 8.6 years. It didn't take any time at all. This is a consequence of Einstein's special relativity. As an object approaches the speed of light, time slows down for it relative to a stationary observer. At exactly the speed of light, time stops completely. A photon travels at light speed. It must because it's massless. And for a massless particle moving at light speed, the elapsed proper time, the time experienced by the particle itself, is exactly 0. The photon that left Sirius 8.6 years ago and arrived at your eye tonight experienced no time between those two events. From its frame of reference, emission and absorption happen simultaneously. The 8.6 light years of space that you perceive between Sirius and your eye. The 8.6 years of travel time that you calculate, these are real from your perspective. But from the photon's perspective, there was no journey. There was no distance. There was no time. Emission and absorption were the same event. This is almost impossible to wrap your mind around, and that's because it genuinely defies human intuition. But it's mathematically consistent and experimentally confirmed. Time dilation at speeds close to light speed has been measured directly using particle accelerators and cosmic ray muons. At exactly light speed, the dilation becomes infinite. Time stops. The photon exists in a state where the concepts of distance and duration simply don't apply from its own frame. It connects 2 points in space-time, the star that emitted it and the eye that absorbed it, without experiencing any separation between them. This means the photon's strangeness isn't just spatial, it's temporal too. Not only can't you say how big it is, you can't even say how long its journey took, because the answer depends on who's asking. From your perspective, the photon traveled for years across light years of space. From the photon's perspective, nothing happened. No time, no distance, no journey. Just a single instantaneous connection between emission and absorption. The photon defies our intuitions about space and about time. It doesn't fit into any simple picture of an object moving through a world. This is quantum mechanics in its purest form. The photon was everywhere the wavefront was, and then it was at one specific point. Both statements are true. They describe different stages of the photon's existence, before and after measurement. Now, let's put some extraordinary comparisons side by side, because seeing them together makes the strangeness vivid. A photon in the cosmic microwave background has a wavelength of about 1 to 2 millimeters. It was emitted when the universe first became transparent, about 380,000 years after the Big Bang. That photon has been traveling for 13.8 billion years. It has crossed the observable universe. Its wave function has spread out over cosmological distances, and it carries an incredibly tiny amount of energy, less than 1,000th of an electron volt. Yet it's still one photon, still one quantum, still indivisible. A photon of green light from a firefly has a wavelength of about 550 nanometers. It carries about 2.25 electron volts of energy, enough to trigger a chemical change in a photoreceptor molecule in your eye. When this photon enters your eye and is absorbed by a rhodopsin molecule, the energy from that single quantum of light changes the shape of the molecule, flipping a small chemical group from one configuration to another. This shape change triggers a cascade of chemical signals that your brain interprets as seeing a flash of light. One photon absorbed by one molecule, creating one neural signal. That's how sensitive your eyes are. Under ideal conditions, the human eye can detect individual photons. You can see single quanta of the electromagnetic field. You are, at this level, a quantum detector. A gamma-ray photon produced in a nuclear reaction might have a wavelength of about 10 femtometers. That's 10 quadrillionths of a meter. That's roughly the diameter of a medium-sized atomic nucleus. It carries millions of electron volts of energy, enough to smash through atoms, ionize matter, and penetrate deep into solid material. These 3 photons have wavelengths that differ by factors of trillions. Their energies differ by factors of billions. One has a wavelength you could measure with a ruler. One has a wavelength you'd need a powerful microscope to see. One has a wavelength smaller than an atom's nucleus. And yet all 3 are the same kind of thing. All 3 are one photon. They obey the same laws. They travel at exactly the same speed through vacuum. They have the same spin. They're all massless. They all exhibit wave-particle duality. They're all indivisible. The fact that one particle can span this range of scales is one of the most remarkable things in all of physics. No everyday object does this. A marble is always roughly a centimeter across, but a photon can have any wavelength at all. There's no minimum and no maximum. The electromagnetic spectrum extends infinitely in both directions, at least as far as we know. This should change how you picture light. Not as a stream of tiny identical bullets, but as quantized ripples in a field that fills the entire universe. Each ripple is one quantum, one indivisible unit of electromagnetic energy. But the character of each ripple varies enormously depending on how it was created, what it's doing, and what you're trying to measure about it. Light is not one thing. It's an infinite family of things, all sharing the same fundamental quantum nature, but differing wildly in their spatial properties. If a photon doesn't have a size, what should we picture when we think about light? The honest answer is that there's no perfect picture, but some pictures are less wrong than others. The worst picture is the little ball, a tiny glowing sphere flying through space. This captures nothing important about what a photon actually is. A better picture is a wave, an oscillating disturbance in a field. This captures the wavelength, the frequency, the interference, but it misses the particle-like aspects. A wave is continuous and divisible. You can't have half a photon. The best picture is something that has aspects of both, but is identical to neither. A quantized wave packet, a localized oscillation in the electromagnetic field that carries one indivisible unit of energy. It has a wavelength, but it's not infinite in extent. It's localized, but it doesn't have sharp edges. It's both everywhere its wave function has non-zero amplitude and nowhere in particular until the moment of measurement. This is hard to visualize, and that's okay. We evolved to understand rocks and rivers and trees. We did not evolve to understand quantum field excitations. When we try to picture a photon using the same mental tools we use to picture a baseball, we fail. Not because we're not smart enough, but because the tools aren't designed for the job. This brings us to perhaps the most profound implication of everything we've discussed. The most familiar thing in the universe, the thing by which we see everything else, is itself something we cannot picture in any ordinary way. Light is the medium of perception. It carries information from the world to your senses. It makes a reality visible. And yet, what a photon actually is, a quantum excitation of the electromagnetic field, has no counterpart in our visual experience. The tool you use to perceive the world is built from components that defy the very perceptual framework they create. Photons give you sight, but photons themselves cannot be seen in the way you see a chair or a tree. You see the effects of photons. You see the world that photons illuminate. But the photons themselves, the quantum objects that carry the information, exist in a realm that transcends your perceptual capacity. We live in a universe where the most common particle, the most abundant thing that exists, is something we can't assign a simple size to. Photons outnumber all other particles in the universe by roughly 1,000,000,000 to 1. They fill all of space. They carry energy from stars to planets. They drive photosynthesis. They power weather systems. They enable communication. They let you see. They are the most important particles in your daily life. And they don't have a size. Think about how deeply woven into your life photons are, and how rarely you notice them. Right now, photons from the sun are streaming through the atmosphere and landing on every outdoor surface, delivering about 1,000 watts of energy per square meter. Each square meter receives roughly 10 to the 21st photons per second. That's about 1,000,000,000,000,000,000 photons hitting every square meter of ground every single second. These photons drive the weather by heating the land and ocean unevenly. They power every plant through photosynthesis, which means they power every animal that eats those plants, which means they power you. The food you ate today was built from carbon dioxide and water using the energy of photons that left the sun 8 minutes earlier. Your body runs on sunlight, one quantum at a time. When you look at a screen, you're seeing photons emitted by LEDs or pixels. When you make a phone call, your voice is converted to a laser signal, photons traveling through a fiber optic cable at the speed of light. When a doctor takes an MRI of your brain, the machine uses radio wave photons to probe the hydrogen atoms in your tissue. When you warm your hands by a fire, infrared photons carry the heat from the flames to your skin. Every moment of your life is saturated with photons, and not one of them has a definite size, not because they're infinitely small, not because they're infinitely large, but because the concept of size, as we understand it from everyday experience, doesn't apply to them. They have wavelengths, energies, coherence lengths, probability distributions. All of these quantities are spatial in nature, but none of them is a size in the way that a diameter is a size. None of them draws a boundary around the photon. The true scale of a photon is not a number. It's an understanding. An understanding that the quantum world operates according to rules fundamentally different from the rules of everyday life. An understanding that particles at this level are not tiny versions of the objects we handle every day. They're something else. Something we can describe with mathematics and test with experiments, but can never fully capture in a mental image. And here's something worth pausing on. The very first science question most children ever ask is some version of what is light. They see sunlight streaming through a window and want to know what it is. They notice their shadow on the ground and want to understand why it's there. They stare at a rainbow and ask where the colors come from. It seems like such a simple question. A child's question. And for most of human history, we gave simple answers. Light is a ray. Light is a wave. Light is a particle. Each answer felt satisfying for a while, until someone looked more carefully and found that it wasn't quite right. What we've discovered tonight is that this seemingly simple, everyday phenomenon, the light by which you see the world, contains within it the entire strangeness of quantum mechanics. You don't need a particle accelerator to encounter the quantum world. You don't need a black hole or a neutron star or a laboratory full of exotic equipment. You encounter it every time you open your eyes. Every photon that enters your retina is a quantum object without a definite size, without a definite position before measurement, exhibiting wave-particle duality, obeying the uncertainty principle, existing as an excitation of a quantum field. The deepest physics in the universe is happening right in front of you, all the time, carried by the most ordinary thing imaginable. Light. The first thing a child notices, and the last thing physics can fully explain. That realization carries a kind of wonder that never fades. Even for physicists who have spent their entire careers studying light. Richard Feynman, who won the Nobel Prize for his work on quantum electrodynamics, the most precise theory of photons ever developed, once said that nobody understands quantum mechanics. He didn't mean that the theory is wrong. He meant that even when you can calculate everything, even when your predictions match experiment to 10 decimal places, the underlying reality remains stubbornly beyond human visualization. You can use the mathematics, you can trust the results, but you can't picture what's happening in the way you can picture a ball flying through the air. The photon lives in a realm where our pictures fail. And Feynman, who understood photons better than almost anyone who has ever lived, was honest enough to admit it. There's something liberating about that honesty. It means the mystery isn't a sign of ignorance, it's a sign that reality is deeper than our evolved brains were built to handle. Every generation of physicists has peeled back another layer. Newton gave us corpuscles, Young gave us waves, Einstein gave us quanta, Heisenberg gave us uncertainty, Dirac and Feynman gave us quantum electrodynamics. Each layer revealed something new and strange, and none of them gave us a simple picture of the photon that we can hold in our minds the way we hold the image of a ball. Maybe no one ever will. Maybe the photon will always be something we can calculate but never fully picture. And maybe that's okay. Maybe that's even beautiful. Because it means the universe still has depths we haven't reached. It means there's still more to discover. It means the simplest question a child can ask, what is light, still leads to the frontier of human knowledge. There's a beautiful irony here. The thing we understand best in all of physics is the thing we can picture least. We can predict exactly what a photon will do in any experimental situation. We can calculate the probability of every outcome with breathtaking precision. But we can't tell you how big it is. The most precisely understood object in the universe is the one that most completely defies our ability to visualize it. Maybe this is what the universe is trying to tell us. Reality at its deepest level is not made of little things with definite properties sitting at definite locations in space. It's made of quantum fields, vibrating and fluctuating, existing in superpositions, obeying precise mathematical laws that we can discover and test, but that we cannot reduce to the simple pictures our brains prefer. The universe is not a collection of objects. It's a web of quantum processes, and the photon, the most basic messenger of this quantum reality, reflects this in every aspect of its being. When you look up at the night sky tonight, you're going to see stars, points of light scattered across the darkness. Each of those points is made of photons that left their parent stars years or decades or centuries ago. Each one is a quantum excitation of the electromagnetic field. Each one has a wavelength that tells you the temperature and composition of the star that emitted it. Each one carries a tiny packet of energy that your retina can absorb, and none of them has a size in the way you imagined before tonight. They're not tiny balls, they're the universe's most fundamental carriers of energy and information, connecting everything in the cosmos through the electromagnetic field that pervades all of space. Every sunrise you've ever watched was painted by these particles that aren't quite particles. Every color you've ever seen was created by photons whose wavelengths fall in the narrow sliver of the electromagnetic spectrum that your eyes happen to detect. Every shadow is a region where photons are absent. Every reflection is photons redirecting off a surface. Your entire visual experience of reality, every image, every color, every flash and glimmer and glow, is built from quanta of the electromagnetic field that do not have a definite size. That's the true scale of a photon. Not big, not small, not a number at all. It's a quantum object whose spatial character depends on its wavelength, its energy, how it was produced, and what you're trying to measure. Its wavelength can be longer than a city or shorter than a nucleus. Its wave function can stretch across continents or be squeezed into a space smaller than a human cell. Its position before measurement is genuinely undefined, a probability spread across space that collapses to a single point only when something absorbs it. It is real. It is measurable. It is the most abundant particle in the universe. And it refuses, absolutely and fundamentally refuses, to be a simple object with a simple size. And that refusal is not a flaw. It's a feature of reality. The photon is the simplest possible example of quantum strangeness. One quantum, one ripple, one indivisible unit of light. And even this simplest case defies our deepest intuitions about what it means for something to exist in space. So the next time someone asks you how big a photon is, you'll know the real answer. Not a number, not a diameter, but a story. A story about fields and quanta and wavelengths and uncertainty. A story about the most familiar thing in the universe turning out to be one of the most mysterious. A story about the limits of human intuition and the power of human understanding. The photon doesn't have a size, but it has something better. It has a nature. A quantum nature that connects it to the deepest structure of reality. And understanding that nature, even imperfectly, even through analogies and approximations that we know aren't quite right, brings us closer to the truth about the universe than any simple measurement ever could. Light has been with us since the beginning of human awareness. It was the first thing we saw when we opened our eyes as infants. It fills our lives. It shapes our experience. It defines our world. And tonight, perhaps for the first time, you're seeing it for what it truly is. Not a stream of tiny glowing balls. Not a smooth, continuous wave, but something in between and beyond both. A quantum excitation of a field that fills all of space. The most common particle in the universe. The fastest thing there is. The medium through which we perceive all of reality. And something that, despite being the most precisely understood object in all of science, stubbornly, beautifully, profoundly refuses to tell us how big it is. That is the true scale of a photon. And it's far more extraordinary than any simple number could ever be. Thank you for taking this journey into the heart of light with me tonight. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the strange and wonderful universe we live in. And remember, the next time you see a beam of sunlight or the glow of a star or the flash of a firefly, you're watching quanta of the electromagnetic field arriving at your eyes, each one without a simple size, each one carrying a tiny indivisible packet of energy, each one connecting you to the deepest structure of reality. The universe is made of light, and light is made of mystery. Good night, and may you never look at a beam of sunlight the same way again.